Here we'll introduce a smart camera to implement compressed sensing spectral domain optical coherence tomography via Optics Group from Tsinghua University, Beijing, China. This presentation includes 4 parts: motivation, method, results, and conclusion. The imaging speed of OCT is higher and higher nowadays. It reaches up to 10 MHz A scan rate for 3D imaging. At such a high speed, OCT data is therefore too massive for transmission and storage. OCT data has a sparsity property, so compressed sensing technique can be used to effectively reduce the amount of data. Compressed sensing was successfully applied in many imaging modalities, such as MRI and photoacoustic tomography. It can also be used in OCT. In recent years, many studies of compressed sensing in OCT were to optimize the compressed sensing algorithm to achieve real-time reconstruction of OCT images. Typically, people use spectral domain OCT to implement the compressed sensing. The spectrum data will fully acquired by CCD camera and then undersampled by software. This means that most of the data will wasted after acquisition. To really reduce the data at the first beginning, a sparse sampled CCD camera is needed. This kind of CCD camera should have randomly arranged pixels and hardwarely undersampled the spectrum. But unfortunately, this kind of CCD camera is not commercially available due to the special requirement. Now the method. This slide shows how we construct the new smart CCD camera. To effectively and randomly undersample this OCT spectrum, we design a mask to block each pixel of the CCD camera. The mask randomly blocks the left half or the right half of each pixel to realize random measurements. This means that each half pixel becomes 1 pixel of the new smart CCD camera. Therefore, the pixel number of the new CCD camera is equivalently doubled, while the line scan rate of the CCD camera remains unchanged. We can also modify the pixel number and the sampling rate by redesigning the mask. The mask can be easily manufactured with the lithography as generally used in nanotechnology. How to put this mask just in front of the CCD pixels is a very critical issue. Obviously, directly placing the mask in front of the pixel like a contact lens is not feasible because it may cause possible damage to the photosensitive surface of the CCD pixel. Another challenge is that the mounting of the mask should have an accuracy of microns. To overcome all the difficulties, we employed a 4F lens system. to image the mask onto the CCD pixels, as shown in the dashed line box. Now the results. We use a mirror as the sample to test the system performance. Compared to the conventional OCT system, the compressed sensing OCT system with the smart CCD camera has better performance, both in imaging depth and signal-to-noise ratio enhancement. The results of imaging at cover glass also indicate the improvement of fall-off and signal-to-noise ratio performance with our new smart CCD camera. For imaging of biological tissues, the compensation OCT system with the new smart CCD camera has deeper imaging depth and higher signal-to-noise ratio. In conclusion, we propose a novel sparse sampled camera, which is fabricated by adding an inexpensive custom-designed mask in front of a commercially available CCD camera. The sparse sampled camera undersamples the spectrum hardwarely and can achieve faster A-scan speed compared to conventional CCD camera with the same pixel number. Compared with conventional SD-OCT system, the CS SD-OCT system equipped with the sparse sampled camera has better fall-off and signal-to-noise ratio performance.